Hi everyone. In the last lecture we have discussed about spectral family generated by a bounded self-adjoint operator. So let us quickly recall the spectral family generated by a self-adjoint operator and some of the important properties, and based on those properties we are going to prove a few more important properties of the spectral family generated by a self-adjoint operator. So let T to be a self-adjoint operator defined on Hilbert space H. Then the spectral family generated by T is a family of projections E lambda, where lambda is coming from R, and here E lambda is nothing but orthogonal projection onto null space of T lambda plus, where T lambda is nothing but T minus lambda I, and by definition T lambda plus is nothing but mod T lambda plus T lambda by 2. So we have seen a few examples and some of the important properties. E lambda is 0 when lambda is strictly less than m suffix t, that is the lower numerical bound of t, and E lambda is identity when lambda is bigger than or equal to the upper numerical bound of t. The second important property that we have proved is the following, that if T is self-adjoint and E lambda is the spectral family generated by T, then if A commutes with T, then we can show that E lambda commutes with A. Now using this we have observed many important results. That the first one is E lambda commutes with T, and then E lambda also commute with T lambda, because T lambda is nothing but T minus lambda I. Now once E lambda commutes with T lambda and E mu commutes with every operator that commutes with T. So E lambda commutes with T, E lambda commutes with T lambda, hence E mu commutes with E lambda, and we have shown that T lambda E lambda is nothing but minus T lambda minus and T lambda into I minus E lambda, that is T lambda plus. Now let us prove few more important properties. Let us write this as a lemma. Let T be a self-adjoint operator and E lambda be the spectral family generated by T. Let us take lambda 1, lambda 2 to be two real numbers with lambda 1 less than or equal to lambda 2. Then we have the following. The first one is E lambda 1 less than or equal to E lambda 2, and the second important property is that E lambda 1 E lambda 2 is nothing but E lambda 1. Okay. So to prove this result we again use the earlier observation that we have made. Okay. So let us look at write P as E lambda 1 into E lambda 2 minus E lambda 1 . So this is nothing but E lambda 1 E lambda 2 minus E lambda 1 square, but E lambda 1 is a orthogonal projection, so this is nothing but E lambda 1. Now in order to show 2 is true, it is enough to show that P is 0. To prove 2, we show that the operator P is 0. Now assume that 2 is true, from that we can show that 1 is true. So assume R2 is true. Then we want to show that E lambda 2 minus E lambda 1 is bigger than or equal to 0. So let us look at E lambda 2 minus E lambda 1. This is E lambda 2 minus E lambda 1 is nothing but E lambda 1 into E lambda 2 by 2. So this is E lambda 2, E lambda 1. E lambda 1 and E lambda 2 commute. So we can write the way we can write E lambda 1, E lambda 2 into E lambda 1, that equal to E lambda 1 into E lambda 2. So here if you take E lambda 2 common, this is I minus E lambda 1. Now we know that E lambda 1, E lambda 2 commutes, hence we can say that E lambda 2 commutes with I minus E lambda 1, and we also know that this is orthogonal projection, hence it is positive. Now this is also positive, and we know that product of two commuting positive operators is positive, hence we can say that this is 0. The reason is that product of two commuting positive operators is positive. So once this is true, that means E lambda 2 minus E lambda 1 is positive, since 1 is proved. So it is enough to show that P is 0, so that both 1 and 2 holds true. Next claim is that P is 0. To show that P is 0, let us take X is in H and write Z as Px. We want to show that Z is 0. Let us consider E lambda 1 into P. This is E lambda 1. P is nothing but E lambda 1 multiplied by E lambda 2 minus E lambda 1. Now E lambda 1 square equal to E lambda 1, because it is an orthogonal projection. This is E lambda 1 multiplied by E lambda 2 minus E lambda 1, but this is nothing but P. So therefore E lambda 1 Z, that means Z is nothing but P of X, that should be P of X again, that is nothing but Z. So let us call this as equation 1. Next let us consider I minus E lambda 2 of P. This is nothing but I minus E lambda 2 into E lambda 1 multiplied by E lambda 2 minus E lambda 1, and this is nothing but I minus E lambda 2 multiplied by E lambda 1, E lambda 2 minus E lambda 1, because E lambda 1 square is E lambda 1. This is E lambda 1, E lambda 2 minus E lambda 1 minus E lambda 2 into E lambda 1 into E lambda 2. Since all these are commuting and we know that E lambda 2 square is E lambda 2, we can conclude that. So you will get E lambda 1 into E lambda 2, and the last term is E lambda 1 into E lambda 2. So we can say these two terms get cancelled, and we can write this as E lambda 1, E lambda 2 minus E lambda 1 square. So this is E lambda 1 multiplied by E lambda 2 minus E lambda 1, and that is nothing but P. Hence we can say that therefore I minus E lambda 2 at Z, that is P of x, is P of x, that is Z. So let us call this as equation 2. Equation 1 is E lambda 1 Z equal to Z. Now if lambda 1 equal to lambda 2, then we can easily say that P is 0, because when lambda 1 equal to lambda 2, by the definition of P it is 0. So let us assume that, next assume that lambda 1 is strictly less than lambda 2. So we want to show that Z is 0. So for that we show that norm Z square is 0. So then if you look at mod lambda 2 minus lambda 1 norm Z square, and this is nothing but lambda 2 minus lambda 1 Z inner product with Z, and this is nothing but, we can add and subtract T. So if you do that, we will get T lambda 1 minus T lambda 2 acting on Z inner product with Z. This is nothing but T lambda 1 Z inner product with Z minus inner product T lambda 2 Z with Z. Now we know that E lambda 1 Z is Z. So let us replace that T lambda 1 E lambda 1 Z inner product Z. So this follows by 1, and minus T lambda 2 Z can be written as I minus E lambda 2 Z inner product with Z, and this follows by 2. Now we know that T lambda E lambda is nothing but minus of T lambda. So you will get minus T lambda 1 minus Z with Z minus, we know that T lambda into I minus E lambda is T lambda plus. So here replace lambda by lambda 2. So this is T lambda 2 plus inner product Z with Z. Now we know that these two operators T lambda minus T lambda 1 minus and T lambda 2 plus are positive, and when you multiply with the minus sign, so on the whole we will get this to be negative. And since lambda 2 is strictly bigger than lambda 1, we can get that Z is 0. Hence Z is 0 or Px is 0. So from this we can conclude that P is 0. This completes the proof of lemma. Now let us look at one more important property of the spectral family generated by T. Let us call this as lemma 4. Let T be a self-adjoint operator, and E lambda, where lambda is coming from R, be the spectral family generated by T. Let us take two real numbers lambda 1 lambda 2 in R with lambda 1 less than or equal to lambda 2. Then we can conclude that lambda 1 multiplied by E lambda 2 minus E lambda 1, this is less than or equal to T multiplied by E lambda 2 minus E lambda 1, this is less than or equal to lambda 2 times E lambda 2 minus E lambda 1. Okay. So, to prove the first inequality, it is enough to show that t minus lambda 1 I multiply e lambda 2 minus e lambda 1 is positive. So, let us consider t lambda 1 into e lambda 2 minus e lambda 1, that is, let us look at t minus lambda 1 I into e lambda 2 minus e lambda 1. This is nothing but t lambda 1 multiplied by e lambda 2 minus e lambda 1. Okay. So, this we can write as t lambda 1 e lambda 2 minus t lambda 1 e lambda 1. This again we can write as t lambda 1 e lambda 2 minus, we know that t lambda e lambda is minus t lambda minus, so this is plus t lambda 1 plus, because t lambda 1 e lambda 1 is minus of t lambda 1 minus. So, here we get this to be minus. So, t lambda 1 we can write as t lambda 1 plus t lambda 1 plus minus t lambda 1 minus multiplied by e lambda 2 plus t lambda 1 minus. So, this is nothing but t lambda 1 plus multiplied by e lambda 2 plus t lambda 1 minus, if you take common, you will get I minus e lambda 2. Now, e lambda 2 commutes with t lambda 1 and hence it commutes with modulus of t lambda 1. From that we can say that e lambda 2 commutes with these two are commuting operators, and t lambda 1 minus is a positive operator and that also commutes with e lambda 2. So, this product of two commuting positive operators, and the first term is also product of two commuting positive operators, hence this is positive and this is also positive. On the whole we will get this is positive. So, here we use the fact that product of two commuting positive operators is positive. Okay. So, so far we have proved 4 lemmas which expresses the properties of the spectral family generated by T. So, let us quickly summarize all these results. Let us take T be a self-adjoint operator and E lambda is the spectral family generated by T, that means they are projections onto null space of T lambda plus, where lambda is in R. Then we have the following: E lambda is nothing but 0 when lambda is less than empty, identity when lambda is bigger than or equal to the upper numerical bound. The second important property, that E lambda commutes with every E mu for every lambda mu in R. So, if A commutes with T, E implies A commutes with E lambda. In fact, from this only the second one follows. When lambda 1 less than or equal to lambda 2, then we have E lambda 1 less than or equal to E lambda 2, and the second important property is E lambda 1 E lambda 2 is nothing but the projection E lambda 1. So, when lambda 1 less than or equal to lambda 2, then we can say that lambda 1 into E lambda 2 minus E lambda 1 less than T into E lambda 2 minus E lambda 1 less than or equal to lambda 2 into E lambda 2 minus E lambda 1. Actually, here the second inequality also can be proved in a similar way, because we have to look at lambda 2 I minus T multiply E lambda 2 minus E lambda 1. So, this is the same way, and using the similar properties whatever we used for T minus lambda 1 into E lambda 2 minus E lambda 1 is positive. We can use the same results to conclude the second inequality also. Okay. So, these are some important results about some important properties of the spectral family generated by T. Okay. Now, we are interested in integrating T with respect to family of projections. The reason for this is that when T is a compact self-adjoint operator, then we were able to express T in terms of linear combination of orthogonal projection onto the corresponding eigenspaces. Now, we also have shown that for a compact self-adjoint operator, spectrum is countable. So, that is the reason we will get countable, we will get a series which expresses the given operator. Now, when the operator is not compact, then the spectrum need not be countable. In that case, the countable sum can be replaced by an integral. So, let me quickly recall. If T is self-adjoint and compact, then T can be written as summation n equal to 1 to infinity lambda n p n, where lambda n's are distinct eigenvalues of T, and Pn is an orthogonal projection onto null space of T minus lambda n I, and we know the series on the right hand side converges to T in the operator norm. And we also know that spectrum of T is exactly set of all lambda n in n union 0 when H is infinite dimensional. Okay. But when T is non-compact and self-adjoint, the spectrum need not be countable. In that case, this summation can be replaced by integral. That means we should know how to integrate a given operator with respect to family of projection. So, let us look at definition. Let T be a self-adjoint operator and A and B are two real numbers with A less than empty and B bigger than or equal to capital MT. Let E lambda in R be a family of projections let us take f to be a continuous function on this interval a b. Then we define f of t, we define the integral f lambda integral a to b f lambda d lambda to be the limit of Riemann Stieltjes sums of the form summation k equal to 1 to n f of lambda I hat e lambda I minus e lambda I minus 1, where this lambda I hat is coming from the interval lambda I minus 1 lambda I. Here the limit is taken with respect to the operator now. So this can be expressed as follows. That means for each epsilon positive there exists a delta greater than 0 such that for any partition P, take lambda not equal to a less than lambda 1 less than so on lambda n equal to p of AB with norm of the partition. Norm of the partition is nothing but maximum of lambda I minus lambda I minus 1 less than I less than n is less than delta so and for any choice of lambda I hat in this interval lambda I minus 1 lambda I, so we have operator norm of a minus summation k equal to 1 to n f of lambda I hat e lambda I minus e lambda I minus 1 is less than epsilon. So in this case we write a is nothing but integral a to b f lambda d lambda. This is an operator. Okay. So let me quickly recall. Suppose T is a self-adjoint operator with a and b are two real numbers such that a less than the lower numerical bound and b is bigger than or equal to upper numerical bound. So if E lambda is a family of projections and f is a continuous function defined on closed interval a b. So we define integral a to b f lambda d lambda to be the operator which is we define this to be a, which is limit of Riemann Stieltjes sums of this kind of operator summation k equal to 1 to n so here summation I equal to 1 to n f lambda I e lambda I minus e lambda I minus 1 this lambda I hat is element in the ith subinterval lambda I minus 1 comma lambda I. We know that this f lambda I is a real number, and E lambda I minus 1, we can easily show that this is an orthogonal projection again. So that means given any positive epsilon, there exists a delta, so that if you take any partition P of AB whose norm is less than delta, and for any choice of lambda I hat in this subinterval lambda I minus 1 comma lambda I, we have this norm of A minus summation I equal to 1 to n f lambda I hat E lambda I minus E lambda I minus 1 is less than epsilon. In this case, this A is nothing but we define A to be integral A to be f lambda dE lambda. So this is the interpretation of the operator integral A to be f lambda dE lambda. Okay. So next we will show that given any self-adjoint bounded operator, there exists a family of projections such that A can be written as integral A to be lambda dE lambda. So those details we can discuss in the next class. I will stop here. Thank you very much.